All right, welcome everybody. This is Fred Schenkelberg, and thanks to today's webinar on environmental and use conditions, which is not testing. And hopefully that'll become clear as we go through a bunch more of this material and so on. Looks like we got a good turnout, a lot of folks in here. It wasn't quite the snazziest of titles. Apparently sample size and Weibull analysis have been the two most popular so far. Yet I think this topic is as or more important than those two tools, than sample size calculations and Weibull analysis. And I believe that'll come clear as we go through the presentation. The gist of this is that our products and services and the things we create exist in the world or in space or in the oceans or somewhere. They exist somewhere. And around them, there are environmental stresses. There are the things around them that impact the ability of our product to function. And those stresses tend to accelerate or interact with or enable, or whatever the right word is. They invoke different failure mechanisms. So the classic one is if we have higher temperatures and there's a chemical reaction that leads to, say, corrosion, it occurs faster. Now, corrosion sometimes requires moisture also, and so it depends. And I hope not to say it depends too many times through this thing, yet we have environmental stresses, and we've got a bevy of failure mechanisms that are all vying to cause a product to fail. And it's that relationship between those two elements, the stresses and the mechanisms, that eventually leads a product to fail. And sometimes it's sooner, and sometimes it's later. And it's a race, really, as to which is going to cause a product to stop functioning. And so the entire piece of what we're going to talk about today is understanding those stresses and those mechanisms and their relationship, and what we can do about that to influence a lot of information or a lot of decisions. The selection of materials, of coatings, of design parameters, of target markets, of, well, you name it, just about everything that we decide during the development process and after, to a large degree, is contingent in part on understanding where and how it's going to be used. And having more information than its ground benign and a handful of quick tables that have min and max values for temperature and humidity, for example, is just not sufficient for product development and all of those decisions that need to be made. And that's what I really want to get after, is that a big part, and for those, and many of you have been to webinars in this series before, and you understand that we need to influence the decision-making process such that the reliability elements are considered, and having great information available for consideration is a big piece of that. Understanding the environments and how it affects our products is a major benefit of what we can contribute to the development process and all of those decisions that are being made. All right, so just in the chat window, we'll get that started off. And Mark's already got ahead of me a little bit. Yeah, shock and vibe in the auto environment. Byman, we'll take a look at that. Mark, so you're looking at temperature killing your present optical chip servers. Yeah, temperature is a very common problem in electronics. There's no doubt about that. Yet there's so many other, just so many other variables out there. Yet, given that there's this temperature, and Mark is a quick example, what other decisions rely on the use of environment and use conditions? Let's see, Dennis is typing. Well, the variation conditions is one of the elements of stress. We're going to talk about that a little later. But what decisions? I mentioned, say, material selection and coating selection, things like that. What else? Yeah, seals or ambient. What about humidity, Jet? It's one of the common stresses that most of our products see. Different parts of the world experience that differently than others. Here in California, we don't have too much humidity. Yeah, Greg, salt spray and corrosion are stresses, but what decisions do those information about salt spray and corrosion, what decisions do those impact? Yeah, materials. If we're going to use something that's prone to corrode from salt spray, we may choose a different material than using the one that's an unprotected steel. We might use stainless instead, for example. So that's what I'm looking for. So we get a lot of listings of stresses. And I think Dennis mentioned mechanical, electrical, and thermal. What decisions? I mean, I talked about ICNR, LCE, I think you mean life cycle engineering. Yeah, whether to do potting or coating, Greg, that's a good one. Yeah? What else? We're in the business of influencing people's decisions, right? So what decisions are we going to try to influence? Maybe I'm not asking that quite right. Yeah, component type. Yeah, warranty period. Yeah, if we know that everything's going to corrode away in 3 months, then a 1-year warranty might not be a good idea. Yeah, raw material selection. You know, if we know that we're going to see 118 degrees Celsius inside the cabinet, we may not use a polyethylene, which has a lower melting or softening point. And it just common sense in that regard. But it includes how it behaves with the range of different stresses that it's going to see. Yeah. Now you're getting it. All right, yeah. Are we going to put enough margin in the product or not, right? And those are decisions that the design engineers have to wrestle with, the safety margin or the derating guides, and in their component selection, in their layout and sealing and so on. All of those elements are decisions that are in part or influenced dramatically by the environment it's going in. Right? If you make say like a Fitbit type device, is it going to get wet or not? That's part of the environment? And if so, what decisions do you need to make about that product? So sealing and coatings and finishes and markings and all of those other elements on it. Is it going to get abraded or scratched or so on? And then it's just, does the product itself perform? So Michael, you're mentioning cooling. Does it create heat and generate heat? Does that need to be dissipated in some way, or removed from the area and so on? Exactly. So I'm hoping to making the point, there's lots and lots of stresses, and many of you listed a good number of them, yet there's also, every stress is going to influence many decisions in the development of a product or system. And so that's what we want to focus on. It's not the list of all possible stresses. And I noticed nobody mentioned fire ants, which is my particular favorite stress. Yet it affected the way underground power meters, the little box on the side of your house or in a cabinet underneath near the street that monitors water flow or power consumption. They found out that on the power boxes that had a electromagnetic field about it that attracted fire ants, and so it dramatically
Press 1
changed.
to enter the conference.
So that dramatically changed the way that the
Press 1 to
seals
enter
were
the
done.
conference.
All right, let me see if I can get rid of this.
Goodbye.
Guess somebody didn't quite make it in that way. And what else do we have here? All right. So I think we're getting the idea there. And so let's talk a little bit about the range of environmental stresses that are out there. And there are quite a few. So the most common one, and the one that we commonly think of, and many of them are listed in when we're listing a variety of different stresses, is the weather. It's the classic stuff that's around our products. It's around us also. The real caveat here is that what you get in your laboratory in Cleveland, Ohio, is probably not the same as what they experience in Denver or in Miami or in Delhi or in Copenhagen. So it's a matter of paying attention to the stresses where your product is being used. And if you're in the lab in a nice controlled environment and ESD and you got great power sources and you're protected from the rain and you're designing an outdoor product, it really makes sense to go put your product outside at some point, see how it behaves. Better if you can do it in areas where your product is expected to be used. Now this is pretty common sense, and yet I've seen that error happen a number of times. The classic weather, there's great databases on the NOAA website and a few other websites that track weather stations all over the world. So if you want to know what the range of weather is and the distribution of temperatures in a particular region, there's databases, public available databases that have scads of data going back decades. And I did that once for a solar power application, and we wanted to know what the weather in California was in general. And it ranges from high mountains to deserts to coastal. And so we broke it up into those different basic regions and compared that to how many installations were going to be in those different regions. And it created for us an envelope that we needed to design within, but it also helped us understand that not everybody sees 45 degrees C all summer long. Very, very few locations in the world actually do that. So if that maps out to where our customers are, then we need to design and deal with it. If it's only one customer out of 100,000 customers, well, maybe it's not worth doing. And so you can see where having that distribution of, say, just temperatures can give you an idea of where the bulk of your product is going to be used. And some companies will design to the 90th percentile. And so instead of a 45 or a 50 degrees C maximum temperature, they may say, well, the 90th percentile in the area that our customers live is only 35 degrees C. And so they design to that range and deal with it. Yeah, and cold too, right? But you know, Dennis, in my apologies for the Canadians on the line, there's not that many people that live in Saskatchewan where it gets to minus 45, minus 50. And the products are protected and used in a different way than they are in Miami. And if you're selling the bulk of your products to folks in Miami,
Press 1 to enter the conference.
somebody is trying to dial in and that's just not working.
Press 1 to enter the conference.
So having not just the min and max, which can
Goodbye.
be very expensive to deal with your design, is understanding the distribution of those weather parameters and where your customers are, and such that you can design appropriately for the vast majority of your customers and not have to worry about the absolute limits. Now, in some cases, the difference between 35C and 45C in your design is immaterial, so you design it to survive 60C and you have plenty of margin. This comes into play when you have that decision on a very expensive part or technology that just can't survive at the 60C or 45C. So you back it off a little bit and understand what your risk is. Now, if you back off too far and it's going to affect 50% of your customers in a meaningful way, well, then you need to talk about that. You need to understand what the risk is and how that's going to map out. But there's other parts to the weather. And somebody earlier mentioned a ionizing, what was that, Ignor? Scrolling back up in the chat window here. Oh, I'm not seeing it. It was a ionizing radiation. I think that was the term. There's a lot out there. There it is. Thanks, Scott. And so radiation, it's ultraviolet from the sun. There's also radiation from other products, electromagnetic radiation and leakage currents and so on, and stray radio waves. Would that affect your product? But there's also things, and I call it power line. It's how good is your power coming in to your system if you have an electronic system that you're plugging in. Power supplies is one of the great banes of reliability engineering because they tend to take a lot of abuse from power line issues. Dips and sags and flickers and brownouts and overpower and underpower, overcurrent, undercurrent. When I worked at Hewlett-Packard, we had a whole range of evaluations and tests to evaluate the robustness of a system to power line variation. And in some parts of the world, it's very, very clean and it's very, very good. In many parts of the world, including where I happen to live, there's plenty of flickers and problems with power. And it can really damage a product. And so spikes and so on can really damage all kinds of components within an electric system. Just because you've got great 120 volt or 240 volt power coming out of the wall doesn't mean that everybody else does. And it can wreak havoc with a product very quickly. So understanding even something as simple as, well, how many lightning strikes are going to be within 2 miles of your customer's location? It was a real question I fielded some years ago. And it was great. Yeah. There is I think it's in Kentucky, there's a national laboratory that actually tracks lightning strikes and frequency of lightning strikes and intensity of lightning strikes. And so you can get all kinds of really good data. And it's not a direct strike that often is a problem. Very few products can actually survive a direct strike. Yet a strike somewhere in the distribution system can send a pulse down the wires. And unless your product can handle those pulses, those electromagnetic pulses that come through, it can cause a lot of damage. And those in the Midwest of the US and other areas with thunderstorms know exactly what I mean, because you've experienced it. So yeah, EMI, electromagnetic interference or electromagnetic radiation. There's also ESD, electrostatic discharge, is part of this unseen yet very real environment that's around our products, and we can consider that part of the weather. Another is chemical exposure. Medical devices in particular tend to be cleaned often, and so it's different chemicals and cleaning solutions and the decision, understanding how it's cleaned and with what kind of chemicals can help you then design the appropriate seals and labels and enclosures and material choices and so on, so that it continues to withstand the very deliberate attempts to clean the units. Now, that's just weather, and there's more to this, and so every product is basically, you have to be your product, a day in the life of your product, essentially, and take note of all of the different things that come at it from outside your product. And one more thing to consider here is that the weather inside your product is just as important as the weather outside your product. And so somebody mentioned cooling earlier. If your product generates a bunch of heat, it's going to be warmer. It might also be drier, which is a good thing in many cases, inside your product. And so the ambient weather in situations around your product line is one consideration. But as you pick components, as you look at what you're going to include in your design, is consider the weather local to that element or product or item within your product. And so there's a lot here, and we're going to talk a little bit more detail in a bit. Critters. I'm going to mention these guys because they're always fun and exciting. I pulled a rat out from the back of an inkjet printer once that chewed through a power line, power cord from the power supply and electrocuted the poor little beast. How it got in there, I have no idea, but believe me, they can get into tight spaces. Fungus and molds in different parts of the world, plants growing into stuff and pulling things apart. Here in California, we have ivy. I know in the southeast they have kudzu that can go in through ventilation vents and really tangle up fans and things like that. There's also dust and debris and flying materials, but there's the insect world, the biological world, the insects and fungus and plants and so on. There's critters and everything from rodents to squirrels to, and you name it. Every one of these critters at one form or another, depending on your application, can cause problems. We had a major power outage at a factory I was at because a squirrel did a dead short in the substation. Completed the circuit. Unfortunate for the squirrel. But it took us out for quite a while, and it took our factory down. But there's also the human critter. Is just as you create a better operating system or a user interface or a stronger button, somebody comes along with a much stronger way to misuse your product, or unintended uses is what we often call it. So thinking through how the human interacts with your product that's a whole other subject for the design element, yet that misuse piece is a part of the environment that our products are going into. Yeah. I'm seeing all kinds of good stories now in the chat window. Those are great. Mice in the car. I remember listening to Click and Clack, the Tappet brothers, and Car Talk, their show, and they had a woman called in and asked how do they get rid of a snake that's curled up in their air conditioning system or in their car, that kind of stuff. Yeah, they're out there, and they will interact with your products, and not often to the benefit of the product, and sometimes not to the benefit of the critter. Now, another element of this weather, the things that our product is that it's not just your inkjet printer sitting nice and snug next to your computer on your desk. It gets transported, it gets moved, it gets dropped, it gets vibrated, it gets stored, and it may be stored in a container, a transit container outside in the full sun. It may get very, very hot. It may get very, very cold. Somebody was talking about Canada and the temperatures they had. But it's also, your product may be like an airplane and have different modes, taxi, flight, and landing, and so on. Other products do this, where they have different loads through the cycle of the day or the cycle of the year. There's so many different ways that our products experience the world around them and get affected by that. So thinking through, and this is not a short list by any means, and basically brainstorming or mind mapping or listing all of these different stresses is a start to this process we're talking about. I already saw a couple of these coming through, things that people have been surprised by. There's so many ways our products can be affected to its detriment that we are continually surprised, and it's always fun seeing this. It's not always temperature, although temperature does affect so many different things. There's so many other ones that are out there. All right, now people use our products, right? And this continues. So when I talk about environmental elements of, say, a reliability goal or of a product development process, I usually phrase it as environment and use, because the way people interact with the product creates a lot of stress that goes into a product. And just its normal use could also be part of its how the stresses interact with your product. So installation in the startup, that initial fire up is where we get the classic dead on arrival type situations. Yet sometimes it's the unboxing installation that's the issue. So, and I've worked with a number of companies where they take products off the loading dock that are being ready to be installed someplace or shipped to a customer, and they take it out and they unbox it and start it up to replicate what the customer would see. And they're looking for any areas where it's difficult to undo, the instructions are not clear, can I miswire something, could I connect a cable the wrong way, can I inadvertently create damage during this transition period of time, and so on. But then also, and this should be done much earlier in the development process, as you start it up or shut it down, does the product itself do that in an orderly, clean, safe way? If you start a lot of electric motors all at once, you may get an inductive load and draw a bunch of current. If that's more current than your circuits can handle, that's a problem. So if your first startup is you blow a fuse every time, there's probably something wrong in the design. Yet the design of the boxes, the installation, the assembly, the sighting, the leveling, you name it, goes into getting it right from the start. And again, here, every product will be slightly different. Also consider how your product's used. Now, this is pretty common sense, right? Is it used once in a while or 24/7? There's the same product used in different ways that could be on either end of the spectrum. So if a product's only used 1 hour once a day in 1 year, it will have different sets of stresses affecting it in its performance, which may or may not limit its life as much or more so than the 24/7 all year long product. So, for example, a computer that's only used an hour once a year is going to have a range of different presenting issues to it and stresses to it than the one that's on all the time. Now, here's a question for you. Which ones is going to succumb to corrosion sooner? If all else is equal, which product was more likely to fail due to corrosion? Yeah, and Dennis, you're exactly right. Just standby mode is yet another variation of this. Is it seeing different stresses? Power on often includes a current surge through much of the circuitry. The first motion of your engine in your car it's one of its first things it does is distribute oil over the mechanisms within your engine to lubricate it. So oftentimes the startup is the most damaging action we do with a vehicle. So again, if we're using it all the time and it's always a warm start, it's not going to see that damage near as much as if it's only used once a year. Right? So I'm kind of piling on here, I understand, but these are all kinds of things that we have to think about. And then a couple of you, I think Dennis, you mentioned it, is the idle time. I saw a presentation years ago at a seminar that Dr. K.C. Siaglu did at University of Arizona, and the presenter was talking about the passenger car and that it's usually sitting still. It's like 80, 90, 95% of the time. They had different numbers for different scenarios of users. And so sitting still in the sun all closed up, and especially in Arizona, the internal temperatures can get really hot. And so dashboard cracking, if you have seen that in cars, it's exacerbated by the high temperatures. If you're in the car and using it and running the air conditioner, have the windows open and so on, it's not near as hot. And so the idle time, just sitting still, still has failure mechanisms at play, and the stresses are different. And so it's a matter for your product to go through a day in the life of your product and note down these different stresses and different elements that are at play with your product. And just a quick note here, which I'm sure you all have a particular. Now, I use the excuse I'm an engineer. I don't even know how to spell, but reading the manual is an admission of defeat. And so that's, yeah. And Mark, yeah, a hot start and cold start test is a great idea to look at those transitions that occur when you're firing something up in different states. And different things can happen. It's interesting how the same exact design will behave differently when it's warm or it's cold. All right, now I want to talk about failure mechanisms, because of all of those stresses, every one of us is probably ticked off and thought of dozens and dozens of ways that those stresses have caused problems. Right? So the stresses in and of themselves, they exist. They're going to exist whether our product is there or not. It's their interaction with the product that's the problem. It's that creation or acceleration or excitement of a failure mechanism. Right? So if we didn't have humidity, a corrosion that required moisture would be less likely or impossible to occur. If we didn't have a voltage gradient, electromigration or dendritic growth, that's the mechanism I'm thinking of. If we didn't have a voltage gradient, dendritic growth wouldn't occur. The metal would not be inspired to move along the gradient. And so for every stress, every environmental and use stress that our product experiences, there's one or more failure mechanisms that it touches, that it excites, that it moves. Now, if it doesn't, then let's not deal with it, right? If the stress doesn't cause a failure mechanism to do anything, or there's no failure mechanisms associated with it, then it's not a problem. Let's not get more information on it, and let's not track it, let's not test for it. On the other hand, some stresses can, like a lightning strike, can immediately damage your product. But in that case, if your product is not a lightning rod, you probably don't need to survive a direct lightning strike. I'm sure there are products that have to do that, but we're not going to design to withstand all stresses. A meteor falling directly on your inkjet printer is probably going to destroy it. Yet we're not going to design for a meteor strike for our next generation of inkjet printers. Some stresses exist, but rare. And in how our products are used, there's other things that cause much more damage more often. And so you can see I'm kind of leading to, we're going to have to prioritize what stresses that we're going to deal with and understand and gather more information about. And understanding how the stresses relate to the failure mechanism allows us to do some meaningful testing if we need to do it. All right, so we're all familiar with failure modes and effects analysis and highly accelerated life testing. And there's been webinars on those in the past, and they're common terms in our industry. One of the results of these activities is to understand that relationship between stresses and failure mechanisms. What causes the problem to occur? And what are those failure mechanisms that we need to deal with? And what are the exciting stresses that cause that failure mechanism to go? And so it is from these kinds of activities and similar activities that we then form a listing, basically, a prioritization of what are those failure mechanisms with associated present stresses in our product's environment that we need to deal with, that we need to make decisions about, that we need to organize and not just test, but design it out, design robustness into the product to deal with it. This is a critical step in understanding the environment and how it impacts the decisions throughout the product lifecycle, especially during the development side. Yeah. Now, and you're right, Dennis, is sometimes people come up with all kinds of weird things that a product can do, yet if there's not an exciting stress, it's not going to happen. Vice versa, we can come up with all kinds of stresses. We can the first half hour of this presentation was about all the weird things that can impact our product. Not all of them are relevant. And so this is a step to narrow that down and focus on those critical few that we need to understand. What we want to do in those cases then is get sufficient information and understanding of that relationship between the stress and where our customers are using it that get that particular humidity, how often do they get that humidity, what kind of moisture content is there, how polluted is the air, if that's a critical factor in it. You can see I'm heading towards a corrosion failure mechanism. Does our coatings and protections for that corrosion, are they effective in the areas that our customers are going to use it? But you can see that we need a good amount of information about our customers' use application and environment where they are, and a bit of understanding about the failure mechanism. And that's where we bring in a lot of expertise as reliability professionals to help that connection, help that modeling. I almost use physics of failure modeling. There's lots and lots of modeling tools out there about failure mechanisms that relate the stresses to the failure. It helps us to either find those in the literature or create them ourselves so that we can articulate our understanding to the design teams. And it's through that information, through that body of knowledge, that we can influence designs and decisions throughout the life cycle that create a more robust product for our customers. All right, here's a quick quiz for you. I think many of you have seen the 85 relative humidity, 85 Celsius test for 100 hours or 1,000 hours. What does that get you? What does that mean? What does that provide at the end of the day? Yeah, Daniela, that's a good question on reading material. There are a good number of books out there. One of them is called on failure mechanisms. It's a physics of failure database, essentially, and it's a collection of papers and references that talk about a wide range of failure mechanisms, and it's called, what is it called? It was done by the RIAC, which I'm sure has changed their name now, WARP, W-A-R-P, database. And I think it's a physics of failure database. That might do it for you. And, you know, and then there's a ton of different books out there. Michael Peck has got a handful of different books, especially in electronics. And I'm looking at my shelf, but it's a little far away to see the titles. Is there a new method to prevent reduced data corruption SSDs? You know, that one's beyond me, Michael. Maybe somebody else will pick up on that one. All right, so David, I think you're talking about this question, 8585. It deals with corrosion. It does. Yet I've seen it. Yeah, and Hassan, it means you pass the standard. Okay, so does your product last for 5 years, or does it last for 5 minutes? Does it guarantee anything? You know, we could do 3 samples or 70 samples, 85, 85 for 100 hours. Well, accelerated aging, but how much does it accelerate, James? What's the acceleration factor here? Yeah, it's not really useful unless you have that connection to a failure mechanism. So some types of corrosion are really excited by this, and there are models out there for it. Some things in other types of corrosion have different rates of reaction to this. And so, well, what kind of corrosion are you worried about? Stress screening. So, I mean, if I'm screening something, Jet, I want to know that it's going to find issues that are relevant to my product. So, again, connect the stress, here it's humidity and temperature, to failure mechanisms. Always, always, always connect those things. So challenge testing. So if I fail this test for 100 hours, it would be a fair question to ask, so what does that mean? We failed it, big deal. Why is that important? And unless you can connect it to a relevant failure mechanism, then it really is a meaningless test, right? So trying to drill that home a little bit, and this is kind of my main thing here. Now, what do we do with all this information? One of the best activities I ever got involved with was creating an environmental manual. Actually, we called it an environmental in-use manual. And what we did is take a look at, and this is when I was working with inkjet printers, is we had a marketing document, actually, that listed the different kinds of customers for this particular class of inkjet printer. There was the office application, the home office application, the home application, the occasional homework application. There was like 5 or 6 different scenarios or avatars for types of users. Now, within each of those situations was a different set of environments. Some had more pet hair and dander and carpet fibers. Office environments had more dust and paper dust, and it got used more often. So they listed the expected pages printed per year, whether it's color or black and white, what kind of mix, and so on. So we added to that by including temperatures and humidities and electrostatic discharge and power line information and the rest of the stresses that were relevant to those different scenarios or locations. So we organized it that way and then broke down the day in the life of a home office application and what would that look like, and both for the weather, the environment part, and the use part, and tried to understand that. But we provided enough detail, not just min-max. We provided distributions whenever we could find one. We tried to provide enough information so that you could make a decision. If you were up against the margin and you couldn't adequately put margin on the maximum value, say, well, what if you backed off 10, 15 degrees, for example, if it was temperature? How many customers would that affect? Now you can see how the relationship between the stress and the failure mechanism, such that I can estimate the change in failure rate, allows me to make very meaningful and financially prudent decisions. Where if I just have a max and we either repass it or not, doesn't really give us enough information to make those trade-off decisions. Because we still have to deal with cost and time to market and usability and industrial design and manufacturability and so on. All of those have to be balanced and traded off. And once we provide enough detail, often just a histogram is all we really need, allows us then to relate a change in the stress or our ability to withstand the stress and its associated failure rates. And then we can make some meaningful decisions with that. The bottom line here is that in that manual, it's not just a list of tests, right? We don't just say 85, 85 for 100 hours. We say we're going to do temperature humidity testing to evaluate the sealing of this particular component for electromigration or a corrosion inside the package. That's its application. That's its failure mechanism. This is how you interpret it. If it passes that test, it's going to be It has a good manufactured seal that should last for 5 years. And here's the evidence that lets us say that. Here's the acceleration factor in the model. If I do 85-85 on something else, and it has a completely different failure mechanism, the interpretation is broken. So simply saying we're going to do, here's the dozen tests we're going to do, without the connection to stress testing, will lead us astray into doing tests that we really don't need to be doing, or they're being done such that they overstress our product and create meaningless failures, or they understress our product and we miss things that are relevant to our decision making. So always, always, always connect the stress to the mechanism and document it, so that every product and every design you do, every development system you work with is then reevaluate, is this test relevant? And that's often the wrong question to ask. I should back up. We have this stress, and it leads to this set of mechanisms. Is that a risk that we need to understand more? Then a test may be useful. So it's narrow it down, make sure you're using your prototypes and test facilities to get more information to influence and improve your ability to make good decisions. It's not a checklist. It's not just run down the list and hope you pass everything. It's really not serving anybody. And so I'm going to catch up with the, looks like somebody found that work database. That's cool. I think it's still out there. Yeah, there's tons of good stuff out there. So, does it not create meaningless failures? Yes, sometimes it does. We take it to the extremes of stress and we finally break it. If that is not that's where part of that process is to understand the failure mechanism. Was it a creep or cumulative damage? Well, then that will occur in the field. Is it just overstress because we hit it way too hard with, say, an overcurrent, and it's like hitting it with a great big sledgehammer? Then yeah, that's probably not relevant. But if we are testing temperature and we expect it to survive in a 40 degrees C environment and it fails at 45 degrees C, I would argue that that's relevant depending on the failure mechanism, right? If we soften some polymers, that's not much margin. We need to deal with that material selection. If we got an overcurrent situation with just a 5 degrees C above our expected, well, there's not much margin there. We probably need to make that product more robust. And so it really is dependent, and I was hoping not to use that too much, on what decision we're trying to make, right? So now a couple of folks are listing different standards and documents that are out there. The problem I have with most of these standards is that they'll list all these environmental pieces and then they'll go right into a test. How do you evaluate this test? And it doesn't talk about what failure mechanism it's relevant for, or what material set it's relevant for, or what use application it's relevant for. And it almost never, very, very rarely, talks about the failure mechanism that it was designed to evaluate. So anytime I look at a standard, I look at, is it connected to failure mechanisms that are relevant for my product? Now, I've told this story before, as I was working with a product that was like a Fitbit, and they found a standard to check it for moisture resistance. It was from the watch industry. They said, well, watches have been around for 100 years, they're well evaluated, they're really robust, they know what they're doing, here's the standard. And the standard said if you want to label your product as water resistant to 1 meter, you need to dunk it in the water, 3 samples, into a bucket of water that's 1 meter deep for 10 seconds, pull it out, shake off the excess liquid from the surface, and check its functionality. If it's still working, this is moments after pulling it out of the water, your product is fine. You pass this test. Now, I don't know, unless you've got, electrolyte-filled water or very polluted water that's very, very corrosive and basically an acid dunk, you can get stuff wet, and electronics will survive for quite a while. Now, what these guys didn't pay attention to is that a week later, all of those samples that they dunked in the water failed. They all corroded. It took them about a week for the corrosive elements to grow and cause the shorts within their product. They weren't evaluating their seals, because it didn't talk about seals in the testing, to see if there was moisture internal to their product. That wasn't listed in the test. They didn't think to consider that corrosion takes a time to occur, especially with relatively low temperatures and voltages. And so they missed it completely and had a disaster of a product launch, because 50,000 out of their 70,000 shipped for the holiday market failed within the first 2 weeks. And it was contingent on them not connecting the stresses to the failure mechanisms and then evaluating that relationship appropriately. And so that the whole idea is, standards are great. They give us a baseline. They give us procedures for doing different activities and testing, to say like a driving rain. How is that defined? Well, there's a standard that defines that. If your product's going to be used indoors or in the dashboard or in a computer room or in space, a driving rain test is probably not relevant, right? And so I think I'll wrap it up with that, is always, always, always connect the failure mechanism to the stress. Then get the information you need to help your company make great decisions, right? The environmental manual is a great way to document it, because if you're making a family of products that are going to be used in the home office, for example, that will go on for many years. And you can continue to evolve and update and improve that document so that it's relevant for every product that's under development and in use. Create the profiles, create the day in the life type information, and connect those to those failure mechanisms. That's how we influence those decisions. That's how we make a real difference with this information. And so that's the presentation. Let me see if I got a summary slide there. A couple of links. By the way, the reliability.fm, the podcast network, just went over 628,000 downloads. We continue to accelerate in downloads and use and comments coming back from that. So if you haven't checked that out, please do. So let's see what else is in the any other questions. I saw a bunch of stuff rolling by on the chat window. Is there anything outstanding I need to catch up with? All right. Well, I'm going to end the recording, and I'm going to stay on the line for any other questions or comments and stuff. So once again, thanks for participating today and for a lot of chat. Really like